Good morning, everybody. I know you're like wondering about the music and stuff, but there's a reason. There's always a reason, right? Okay. I don't know about you, but this is the music that plays anytime I enter a room. No? All right. I've been handing out lab packets, so if you've been coming in late, be sure to get one either on your way out or you can come up and grab one right now. Why am I playing music this morning? Because we're going to learn where this comes from, right? We're going to learn the physics of music today, right? But before we do that, let's play a game of Name That Tune. Oh boy. Okay, so the conditions here are, right, that I can't play anything that is not a part of like orchestral music. The reason being is that like electric guitars and synthesizers and things like that, that's all physics 2B, okay? Because we need some more understanding of how electromagnetic fields work before we can talk about those forms of music. So we're going acoustical only, and I know that there's modern acoustical music, but I will kind of limit this to the orchestra. And I know I'm, showing my old manness by doing classical music, but honestly, I've been listening to this stuff since I was 4, so, whatever it takes. Let's see. Can you name, let's do this one. I'm sorry, like this is the Moonlight Sonata by Beethoven, okay? It is quite possibly one of the most haunting music pieces, right, on the solo piano. It's incredibly beautiful, and I have heard it so many times that I am tired of it. Like beginning piano, my wife's music teacher, like beginning piano students just play over and over and over and over again. So we're not here to talk about Beethoven or my emotional response to this music. What instrument is that? Piano. How do you know? Sounds like a piano. All right. Those are violins. What's that? It's actually a flute, but. How do you know it was different? It sounded different, Mr. It's not a piano, right? Okay, right? So we're going to be talking about how we can tell the difference between musical instruments and their voices, because this all comes straight back to the physics of what's going on with standing waves. But since we're here, let's play another Name That Tune. Okay, so this, I gotta scrub forward in this music a little bit to find the part that you probably are familiar with. We'll get there. Where is it? It's right about. Have you heard this before? I'm guessing if you haven't taken like music appreciation, if you're not a classical nerd, you probably have not heard this before. But you think you've heard it before because it sounds like something. What does it sound like? Like what?
Sounds like DreamWorks.
DreamWorks, like movie music, right? It's got kind of that sort of big, heroic, Dances with Wolves, or the buffalo roaming the plains, or the superheroes celebrating their victory on the bodies of their enemies, whatever, right? It's got that feel to it, okay? Does anybody think they know what this piece of music actually is?
Is it the planet?
Yes, it's from the planets.
And it's the one from before. Is it the Carnival of Animals?
Very good, Carnival. You get the A for today. okay? Because the one I was playing before was the aviary from Carnival of the Animals. So this one I was just playing was from the planets. Which planet? Good, Jupiter, A+, right? So in 1906, 03, 04, one of the 1900s, Gustav Holst wrote a series of musical pieces, 8 of them because there were only 8 planets at that point, and there's still only 8 planets, and we can fight about Pluto later. Wrote a series of musical pieces, and each one of the musical pieces was like an 8-part symphony, and each part was a different planet, okay? And what I just played for you was Jupiter. Now, in Greco-Roman mythology, Jupiter was Zeus, and Zeus was, the big guy on top of Olympus. And so the music was supposed to be evocative of like the grandeur of Zeus. He's very heroic, right? All that kind of stuff, okay? So I'm going to play another part from the planets here, okay? And I want to see if you can guess which planet this is. I know you know, so don't say.
Mercury or Venus.
Mercury or Venus. Okay. It's building a little bit right here. What's your emotional response to this music right now?
Scared.
Kind of scary? Kind of, should I be playing this right before an exam? No? Because this music has a bit of like these speakers suck, so you can't really hear the bass, but there's this ominous, like, dreadful, something's gonna happen to me, right? Okay? So now listen to this part coming up. This is gonna sound really familiar. Here it comes. It's coming. It's coming. It's going to get you. It's going to get you. Here it comes. What was that? It's Star Wars. It's not Star Wars. That was Mars by Gustav Holst. Mars, the god of war, right? And so it's supposed to be this dreadful, So when John Williams sit down and he's like, okay, got to write music for the evil empire, right? Okay. Well, maybe I shouldn't put an evil empire on there because are they rebels or terrorists? Anyway, well, let's not get into that, okay? Right? But like when John Williams sits down to write the Imperial March, what does he reach for? Where have you heard that? It's in Mars, isn't it? Like, this is a music nerd's dream, right? This is like an Easter egg, right? Okay? Because anybody that knows the planets knows what John Williams did here, right? Okay? Like, it's really, really cool, right? What he was able to do. So music kind of has that power, but the music itself, the physics of the music, how that's generated, how it moves through the air, how we respond to it physically, not just emotionally, but like how our ears and our brains like cue into the music is really, really fascinating. And of course, I'm going to make it all boring by giving it a whole bunch of physics, right? But I hope by the end you have a greater appreciation for sound and how it's formed and all of those kinds of things. By the way, John Williams, totally like the Mozart and Beethoven of our day. Like no contest, right? I mean, he borrowed a lot of music from other composers on purpose. It was a wink. But some of his original compositions and the stuff he did in movies is really, really incredible. As music, okay? Not just, because of the movie or any of that kind of stuff. So what we're going to do is we're going to move towards standing waves in pipes, okay? And These are standing waves. We say standing waves in pipes, but they're standing waves in air. Now, what kind of wave is a sound wave? Transverse or longitudinal? Do you remember? It's longitudinal because only longitudinal waves can travel in a fluid. So when we did the standing waves yesterday on the string, we had a transverse wave going up and down the string, right? And transverse means that the wave is wiggling like perpendicular to the direction it's like traveling. So what is a longitudinal, first of all, what does a longitudinal wave even look like? That's a problem, okay? It's really hard to visualize. And then so how do you visualize a longitudinal wave? And then how do you visualize a longitudinal standing wave, right? Okay, so we're going to fall back on nodes and antinodes and all of that stuff, but we've got to kind of do sort of a wink, wink, right? We're going to draw pictures of transverse waves when in fact they're really longitudinal waves. But I'll sort that out here in a minute. What I want to do is I want to show you a video where they are going to generate standing waves in a column of air inside of a pipe. It's just that this pipe has had some cork dust sprinkled at the bottom of it. So as these standing waves form that they're going to generate, we're going to see the dust in the pipe do stuff based on where the nodes and antinodes in the pipe are. This is like the closest we can get to like showing you what a standing wave in air looks like. Unfortunately, in this video, to make these standing waves happen, they have to produce a sound that's very close to like fingernails on a chalkboard. Okay? So I'm warning you ahead of time, right? And I'm going to turn the volume down just a little bit because it is kind of one of those sounds where you're just like, I don't want to hear it anymore.
We'll use this long glass tube and some cork.
I'll talk. There we go. Okay. So she's got to put alcohol in a cloth and then rub the alcohol on the metal rod to generate the awful, awful sound. Okay. That is the standing wave. Okay. And for those of you that can hear high frequencies, you can probably still hear it. Right. But if we watch the cork dust, right, you can see sections here where it like really kind of jumps a lot and then other places where the cork dust doesn't move at all. So which one is the node? Where it doesn't move at all, right? And then where we saw those kind of the cork dust really jumping around when they would generate the wave, that would be like an antinode. So that's one way to think about like standing waves in air. It's places where like, and instead of cork dust, you think of air molecules, right? A node would be a place where the air molecules are not moving. Like normally compression waves, right? They do something like this, right? But in a node, you've got just air not doing anything. And then right next to it, you've got air kind of wiggling back and forth a lot. And then you got air doing nothing. And then another place, you got air wiggling a lot, and then air, right? Node, antinode, node, antinode, node, antinode, all the way along. So these standing waves in pipes can be a little tricky to like really visualize, so that's why we're not going to come up with a new visualization. We're actually going to use our old standing wave pictures. We got to adjust something, and we'll get to that adjustment here in a minute. But we're going to, even though these are longitudinal waves, you're going to see me draw footballs again. Okay? So we want to capture the node, antinode, node, all that stuff, right? But we want to do it with an understanding that what we have here are these ways. Okay, so this picture is trying to show you how to generate like a traveling compression wave. You have to have something. In this case, it's like a piston, right? It pushes on the air, and then that compression sort of just travels along, right? And right behind it, there'll be another compression coming along, another compression coming along. So this is just traveling, right? Air in a pipe. In a musical instrument, there isn't a piston, right, to cause the vibration at one end. Anybody here play like trumpets, woodwinds, any of that kind of stuff? Yeah, okay. What do you play? Clarinet. So in your clarinet, right, what do you have to put on the mouthpiece in order to get it to work? You have a reed, right? And they're either made of bamboo or more probably today a synthetic plastic. But I played clarinet, so I know all about reeds and what reed number, what size? 2.5, very common reed size, right? And the different reed sizes let you reach different registers. Anyway, okay, so you put this reed on this mouthpiece, and then you got to get that embouchure just right, don't you? Right? In order to, so playing the clarinet, you either play the clarinet or you're killing a goose, right? There's really no in between, okay? So you're going to be playing this wonderful clarinet piece when all of a sudden a goose dies. Because if you get the squeak or you get the reed wrong or something like that. But it's the reed that causes the vibration. It's like the plunger at the end of a pipe. And of course the clarinet is actually a pipe, okay? In a trumpet, the vibrating end, right, is done by the lips, okay? I got to remember to turn because otherwise you guys get wet, okay? Because trumpet, anybody play trumpet in here? French horn, close enough, right? Because one of the features of both trumpets and French horns and a lot of the other brass instruments is they have a valve, a very special valve that, you never had a valve on your French horn that let the
spit valve.
The spit valve, right? Okay. What's the spit valve do? It lets the spit out. You can get a point when playing the trumpet or French horn or something where you are literally trying to blow against a puddle of spit that's sitting at the bottom of the instrument, right? Okay. So yeah, music is gross. And a lot of fun and all that kind of stuff. All right, so saxophones use reeds, trumpets use their lips. Okay. Oh boy, what's going on? Oh boy. Okay. First big change. Okay, there are two kinds of pipes in the universe. Physicists we try to boil down very complicated things into very simple structures. And so what we've done is we've discovered that for creating sounds in air with musical instruments in a woodwind instrument, again, where you've got a standing wave that's forming in a column of air, there's really two kinds of pipe you can have. An open pipe and a closed pipe. The open pipe means open on both ends. So like you go down to the hardware store and you buy a pipe, they usually don't come with caps on either end, right? It's usually just a nice open pipe, okay? And then there is the closed pipe. And I want to be very clear here. You need to be very careful. Closed pipe means closed on one end. I'll picture one of those in a bit, okay? It's not closed on both ends, because if it's closed on both ends, no music. A pipe closed on both ends is a pipe bomb or similar, right? Like it's not, you're not making it. Okay, there's one exception to that rule. And if you are of the American cultural persuasion where singing can only happen in the shower, then you are singing inside of a closed pipe. The shower is closed on all sides, in theory, right? And the sound waves reverberate off the shower curtain and off the walls and all that kind of stuff. You're in a pipe that's closed, and you can hear what's going on because you're inside the pipe, right? But if we make a musical instrument that's closed on both ends, nobody's going to hear anything, right? So, and it turns out that the pipe closed on both ends has exactly the same mathematical physics as standing waves on a string. So we've actually already did that one. But it's an exception, it's not the rule. So let's do an open pipe, okay? And we know it's an open pipe because both ends are open to the wider universe, which means that the air molecules are free to wiggle there. And what did we learn about wiggling air molecules? Are those nodes or antinodes? They're antinodes. So what we have here is a pattern where the pipe has to have an antinode at each end. When we drew the pictures yesterday, remember we had to have nodes on either end, and our fundamental had one antinode. So here the fundamental has an antinode on either end and a node in between. And we call that the first harmonic. For a pipe open on both ends, do we count antinodes or nodes? The first harmonic has one node. The second harmonic has two nodes. The third harmonic has three nodes. Okay, so the rules are changing a little bit, aren't they? On a string, we count the number of antinodes, and we know which harmonic we're on. But for a pipe open at both ends, what do we count instead? Number of nodes. So that's kind of our first change. All right. It's kind of hard to see on the screen, but the wavelength, right, looks like it's doing about the same thing. This one's a slightly different picture, and they're solving directly for the wavelength. But it is going up by half every single time. And as you can see, the fundamental V over 2L, once, twice, three, right? Just multiples of N there, okay? So for the open pipe, what does our toolbox look like, okay? So first is count nodes, right? You want to make sure you're counting the nodes to know which harmonic you're on. Your fundamental frequency is going to be V over 2L, just like it was for standing waves on a string. Your nth harmonic is going to be N times whatever the fundamental frequency is. And then your wavelength is going to be, I don't remember what the other equation, 2L over N. Is that what it was? Thank you. I think it was 2L over N. I've got it right here. Why don't I just go back and look? This is why we take notes, right? 2L over N. So, have we learned any new equations? No. Okay? We actually have exactly the same mathematical pattern for a pipe open at both ends as we do for waves on a string. What's the important distinction? Count the nodes to figure out which harmonic you are on. Now, how do you draw these? Okay, I say, this is what I do. I still kind of draw footballs, but instead of like a football shape, I kind of do like I do a half football, right? Because I've got to have a node, right, and then I can draw another half football. This starts to get just tedious after a while. So sometimes what I'll do is I'll just go node, 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 right? And then know that I've got to put antinodes on the ends, right? And that kind of becomes my picture, right? Just to sort of center my brain on how many nodes are there, like what harmonic am I on, right? All that kind of stuff, okay? So, and notice, do you see how even in this picture we're drawing transverse waves? Are these waves transverse waves? No, they're waves in air, right? And what's more, they're standing waves in air, right? So they're actually not going anywhere. There's nodes and antinodes. It's just, it becomes really, like, do you just draw like, right? No, we don't do that, okay? So, yeah, draw half footballs or draw a node antinode pattern, or I don't know, just go bananas. But that's not how you spell banana. But you get the idea, right? All right. But bottom line, open on both ends, same toolbox. Count the number of nodes, you're good. Where life falls apart is the pipe closed on one end. Because we actually fundamentally alter the physics of the situation here. And by that I mean, on the open end, it has to be an antinode. That's a place where the air is very free to wiggle around, so that's going to be an antinode. But when you hit a closed wall, That's a place where air molecules can't wiggle. They just run into an obstacle. And so you have an antinode on one end and a node on the other, which means your first harmonic in the pattern of I've got an antinode here and I have a node here. What this means is there is only 1/4 of a wavelength. Remember a wavelength, right? Come up and down, right? And if you go from a peak, like the top of an antinode, to a node, you've only covered 1/4 of the waveform there. So in the pipe of length L, we can actually fit, it's only 1/4 of the wavelength. And so if this pipe were 1 meter long, this fundamental wavelength would be 4 meters. So on a string and on a pipe that was open on both ends, what reigned supreme were the factors of a half as we went down. Well, here you can see it. There's factors of 4 sitting places, right? And I don't kind of want to get into too much of this. So our fundamental, come here, come on. Our fundamental is that. That's like the lowest. You can't have an antinode all by itself. You can't have a node all by itself. So the simplest pattern you can have is antinode node. But to get to the next pattern, again, remember, one end has to be an antinode and the other end has to be a node. So can I just add an antinode? No, this isn't going to work because this is an open pipe pattern, isn't it? Where it's antinodes on both ends. I'm forced to add like a complete pair. Node-antinode pair has to go in there, right? And so we've gone from like 1/4 to 3/4. It's a peak, center, trough, back to center. That's 3/4 of a wave. The next one's going to be 5/4. So not only is it going up by fourths, but it's only going up by odd multiples of fourths. So the first one is 1/4. But the next harmonic is 3/4. The harmonic after that is 5/4. What's the next one going to be? 7/4. This is just a consequence of looking at the physics of what the waves can do inside of a closed pipe. So that means, so what do we count? So the first harmonic has one antinode node. The third harmonic has 2 antinodes and 2 nodes. The fifth one has got 3 of each.
You add them all to subtract.
Just give up. Okay, give up on counting when it comes to closed pipes. Like seriously, okay? You really don't want to go in and count. I mean, what Brandon just said is true. You can kind of add them all up and subtract 1, or right? But I just see closed pipe, and I just sort of like clench everything up and go for it, right? I'm just gonna hold to the toolbox and see what comes out. Okay. So what do you count? Don't know. Okay. Importantly, the fundamental frequency is V over 4L. That's like really critical. This is where people mess up most when dealing with standing waves in pipes, is confusing open and closed pipe equations. And it's really easy because one of them's over 2L and the other one's over 4L. And those are all even numbers and multiples of each other. And it's just awful. Okay? So, and it's also true that you can find whatever harmonic you're on by just multiplying the harmonic number. But I mentioned it, but what have you noticed about how they're counting here? It's only odds, isn't it? So N is odd only. In a closed pipe, there are no even harmonics. There are only odd harmonics. There's a lot of implications that we've got to cover over this. But I've got to ram home and get your brain to realize when we're talking about closed pipes, as soon as you see the word closed pipe, or if you're told that a pipe only has odd harmonics in it, you instantly know that's a closed pipe, meaning the pipe is closed on one end. Okay. I don't honestly know how to teach this next part. 24 years and I'm still trying to figure out a way to sufficiently apologize on behalf of all of the physicists that have tried to make this work, and then now it is just a mess of terminology, okay? There are so many words that are used to describe harmonics in standing wave systems. And where it gets really confusing is closed pipes. What do I mean by that? Most textbooks nowadays, the last 10, 15 years or so, have standardized on the word harmonic, meaning the actual number that you are on. So when you say seventh harmonic, we know that n equals 7. And that makes sense, right? That's just natural, okay? But prior to that, and you'll still see it, like I've seen ChatGPT throw this one out constantly, okay? Because again, it's just doing statistical matches of things. There is an older system, and still some physicists today who are younger than me that I would like to throttle for long periods of time, who insist on the first harmonic being called the first harmonic, and then what we would call the second harmonic, they call the first harmonic. Because their argument is a harmonic is a multiple of the fundamental. So if you're talking to somebody that's using that system, right, and they say the second harmonic, what n value are they talking about? 3. You have got to be kidding me, right? I have trouble enough with numbers and remembering them, and now I've got to remember to shift by 1 everywhere I go. It gets worse, okay? The second harmonic to these, I was going to call them people, but really they're just aliens, okay? The second harmonic of a closed pipe under that system is what we would call the third harmonic. And what would the third harmonic be for them? Be n equals 5 for us. It's like, it's messed up. Like that system is messed up. And it's the one I had to learn in college, and I would like to go back and talk to that professor, okay? Because it is just a messy system. I understand it maybe was the one that was used for 150 years, blah, 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 blah. That doesn't mean it's garbage, right? Use the harmonic number that corresponds with the n value you are talking about. To make matters worse, there's another system called the overtone system. This one arose out of a desire to get the two sides to talk to each other. And so they'll refer to the first harmonic and then the first overtone and the second overtone. But that's still bad because you're off by 1. Okay? So you'll see that one crop up every once in a while. And I think with the age of AI, we're going to start seeing a lot of these systems come back, and students are going to be so horribly confused. In my class, I promise you, this day, I am not going to try to confuse you on an exam. Right? If I say the 7th harmonic, what do you now know? N equals 7. Right? That's it. I'm not going to play games, right, with all these different systems. The reason I have to tell you about them is because the internet exists, right? And I can't just I can't contain your knowledge to your book. right? It's one of the things we lost with Google, right? Is the ability to really just have students focused and all on the same literal physical page when it came to the information, right? So now we're spending a lot of our time as teachers trying to help students sort out the fact that, you know, V sub I and V naught are really the same thing, right? So you're getting more flexible in like understanding symbology, but it takes a little bit more brain power. So we got the overtone system, we got the harmonic system. How do you know which one is which? And then on top of all of that, physics textbook authors try to be clever in the problems. And this I can't really save you from because even Wiley Plus does this. And so I've got some examples in the ones I'm going to do today. They'll say the fourth resonance of a closed pipe. What's the fourth harmonic of a closed pipe? I think Brandon beat me to it. Let's see. You have the fundamental, and then it goes n equals 3, 5, 7, 9, so on and so forth, right? This would be the first resonance. This would be the second resonance. This would be the third resonance, and this would be the fourth. Oh my gosh. And that's if they define resonance as starting with the third harmonic. What if they define the fundamental as the primary resonance? Because I've seen that too. So, once again, I apologize. Maybe I've taught you too much, but I wanted you to be prepared, right? I wanted you to realize that there really isn't any kind of standard terminology when it comes to standing waves in pipes, right? It just isn't, okay? So we've been trying, like I said, in the last 15 years, a majority of physics textbook authors have settled on just use the number for the harmonic. Like, don't try to do all this screwy games, mental games, right? It doesn't get us anywhere. People can't learn anything if we're screwing all this up. But it is a relatively new convention, and convention would be a really strong word for what's been going on, okay? I believe the wavelength is 4L over N. Generally what you do with pipes is you use frequencies, you solve for frequencies, and then it's just V equals lambda F, and the speed is the speed of sound in air. So 343, and you can go figure it out. But I hope I'm right. I'm pretty sure that's what it is. But what does N have to be? Odd. Really, really important, right? For closed pipe, forget about counting anything. And then make sure that any harmonic numbers you are using are odd only, irrespective of what system the problem or the web page or ChatGPT happens to decide to use that day. I felt like there was something else I needed to tell you, but I don't remember what it is. So we'll just keep going. It'll probably occur to me as I go, if there was something. All right. Visualize, strategize, do it, check it, right? Just same approach, different details, okay? So fundamental frequency. Well, that's F1. It's the lowest frequency that can form in the pipe, okay? It happens to be middle C, which is 261.6 hertz. So what do we know about this particular frequency? Like, what do we know about the pipe that is making this frequency? This is an open pipe, right? Okay, and here we go. I did this on purpose. The third resonance of a closed pipe, okay? I actually pulled this problem out of a textbook, okay? And then I went and I solved it, and I got it wrong. Because I assumed that for the closed pipe, the third resonance, remember the pattern is 1, 3, 5, 7, 9, right? I assumed that you have the fundamental, and then you have your first resonance, second resonance, third resonance, right? I went and I solved and I got it wrong. And my only way to figure out what was going on was to go look at the key. That's how messed up these words are, okay? Because the author, graduate student, monkey, whoever it was that solved the problem, okay, decided that the fundamental was the first resonance. So the third resonance was going to be n equals 5. I point this out because you're going to get frustrated on your homework, right? And you're going to be reading it, or maybe you've seen another website or Khan Academy, or you've asked ChatGPT or one of the AIs to give you some more practice problems or something. And they'll throw this out, and then you'll be like, wait, I thought the third resonance was 7, not 5. Please, please don't assume you are stupid, because you are not. What's stupid is the disagreement over that term that we're using, resonance, right, to describe what's going on. So I wanted to just let you be aware, know that this is a problem. And for a science like physics that is so exact and uses really precise terminology, as soon as you get into acoustics, it's like the Wild West, okay, of terminology. Acoustical physicists are weird, and I can say that with authority because my brother-in-law is one. He's a good guy. Weird, but a good guy. All right, so so they said third resonance, right? And to them, that meant that. Like I said, I hereby solemnly swear that I will not pull this trick on you in an exam, right? Even if to the point where you are unclear, right? You're reading the problem and you don't understand what resonance you're supposed to be doing, throw your hand in the air, walk over, Mr. Balogh, what are you talking about? And I'll just tell you the number. Hopefully I will have done that anyway in the problem, right? But I'll just tell you. Okay. Sometimes I copy paste from different test banks and I don't realize, I see the word resonance and it just goes through my brain as, oh yeah, closed pipe, right? And I don't think about it too much. And then when I go to solve the problem, again, it doesn't flub me up because I'm used to dealing with this problem, right? But you guys just need to ask. I will always make it clear. Okay. Now, if I tell you that there are 4 antinodes, right, on the string, and you ask me, well, what's my harmonic? I won't tell you that because I expect you to know that with 4 antinodes on a string, that's n equals 4. Okay. Practice. Okay, what do we know? Okay, so all of that, what are they trying to say? Okay, so they're trying to say that the 5th harmonic, the third resonance, okay, is the same frequency as the other pipe that was open on both ends that had its fundamental. The third resonance, in other words, n equals 5, of a closed organ pipe has the same frequency. Same frequency meaning this number up here, okay? And what they want us to find are the lengths of both of these pipes. Really, the kind of the only operative equation we have when it comes to frequency and length, right, is this one for, I shouldn't have drawn it right there, this one for open pipes, and this one for closed pipes. What are we going to put in for the speed of these waves? 343. For standing waves in pipes, these are standing waves that are forming in air. And the speed of a wave depends on the medium in which it's traveling. And when you're not told anything about that medium or its properties or what the speed or temperature or anything is, then you just assume 343 meters per second. Okay, so now we do algebra. Like our strategy is solve each of these equations for L and figure out what it is. Okay, so this equation right here is going to become the fundamental is equal to V over 2L. And L then will be V over twice the frequency. 343 divided by 2 times 261.6. I got 0.656. No. I got 1.31. I was reading the wrong number. Okay. So is it 1.31? No. No, it's 0.656. I just can't read. 0.656. Okay. I just can't. I've got two numbers on here, and there's a scribble next to one of them, and I can't figure out what's going on. So 0.656. All right, meters. All right, so there's the length of the open pipe. Over here, the closed pipe. Our N is 5. So F5 is equal to 5V over 4L. So the L is going to be 5V over 4 times whatever the fifth frequency is. 5 times 343 all over 4 times 261.6 will get me 1.64. I hope. I should learn to write bigger. Actually, I probably wrote this note a long time ago and I could see. 1.64. It is 1.64? Okay, good. All right. Okay. Is the math difficult? Like compared to things we've done in this class, this is like kindergarten math, isn't it? Like divide. If you can divide, you're good, right? It's not the math that's hard. It's sorting through the terminology and the language, right? And then making sure that we use the correct equation for the situation that we have. The good news is, whether it's a standing wave on a string or a standing wave in an open pipe, those equations are the same. The one time it changes is for that closed pipe, right? And closed pipes is kind of where it all goes wrong, right? We don't really know what to count. So we don't know, right? We can't do it that way. And then there's this whole weird like overtone resonance problem that Mr. Balogh was talking about, and I still don't understand what's going on. Come into grass and get help. Okay? And we'll try to steer you correctly. Okay? So here's, again, just another problem, right, that's dealing with these equations for standing waves in a pipe. Okay? And then we're going to get back to the orchestra. So a metal pipe, the problem doesn't start off by talking about whether this pipe is open or closed. When they don't tell you, just assume it's open on both ends. Because, again, most pipes don't come from the factory sealed on both ends. Okay? They come open. So we've got this metal pipe. And it says it's cut in two pieces. It doesn't say that it's cut in half. And in fact, I know that it's not cut in half where the lengths should be equal because there's two different frequencies that are sounding here. And the frequency of a pipe depends on the length of the pipe. The longer the pipe, the lower the frequency, the fundamental frequency that is in there. So that's why tubas are really big and sound really low notes, okay? A tuba is big because they've got to wrap. Like if you unwrap a tuba, okay? I can't remember. It's like 35 feet long or something like that, okay? It's just really long. Your French horn is like 17 feet long when it's like unwrapped. Like it's like trumpets are like 12 feet long when you unwrap them, right? And you actually kind of get all, right? Yeah, they're long. It's just that they're compacted by twisting them around on themselves, right? Clarinets are as long as they look. Flutes are as long as they look. Oboes are as long as they look, okay? So it says here that it's cut into two pieces, but it's definitely not equal. One of these pieces is going to be longer than the other, and the longer one is sounding the lower frequency. So the short one is 440 hertz, and the long one is 256 hertz. Okay. So we need to find the fundamental frequency of the original, and then how long the original pipe was. We're actually going to do that in reverse. We're going to find the length of the original pipe first, and then we can go find its fundamental frequency. No, you can't add hertz like this, okay? Because these are different lengths sounding different fundamental frequencies. So we know the fundamental over here is V over 2L, right? Same thing here. Fundamentals V over 2L. And so what we know the frequencies and we know the speed of sound. So we can use these equations to find the lengths of the pipe for us. Once we find the length, we can find the original length of the pipe and then find its fundamental frequency. So that's my strategy here, right? So the length is V over 2 times the fundamental. Same thing over here. It's exactly the same math. This length will be 343 over 2 times 440. Anybody know what 440 is? What note? No orchestra player. It's A 440. It's the A above middle C. It's the A that the entire band or orchestra tunes to when they tune at the very beginning. If you haven't been to an orchestra or band concert before, it's a ritual, but it's also a very important thing to do. Otherwise, the music isn't going to sound right. You got to make sure every instrument, when it plays a C or plays an A or whatever, is playing the same note. Otherwise, it sounds bad. And so what will happen before the conductor comes out is either the first violinist in the violins, or I can't remember, first oboe. I can't remember who does it in a band. But does anybody know the difference between a band and an orchestra? No strings in the band, right? In a band, it's just woodwinds, okay? It's because nobody likes the strings. Sorry if you play a string instrument. So they'll come out and they'll play a note, okay, and it's A440. And then all the instruments will tune to it, okay? That whole process is actually a lie. Because the orchestra or the band has actually already tuned probably about an hour before any of the people come into the room to listen to the concert. What instrument did they tune to? Does anybody know? The oboe. Yeah, the oboe. And sometimes, if the orchestra really just, doesn't care what, people see how the sausage is made, the first violinist will come out, take his or her bow, and point at the oboist with the bow. And then the oboist will stand out, play A440, and then the entire rest of the orchestra will tune to it. You can't tune pianos on the fly, so that just gets tuned earlier. Okay? Why the oboe? Does anybody here play oboe? No? It's impossible to tune an oboe. Like it's really hard to tune an oboe. And so you take the instrument that's the hardest to tune or change the tuning of, and you let it set the note for everybody. And then I'm reminded of a joke. My wife is a flute teacher, a performance major, and all flautists also play piccolos. And piccolo is the other one that's like really hard to tune. And so there's a joke amongst flute and piccolo players. How do you tune two piccolos? You shoot one of them. It's not a lie. Like piccolos always sound out of tune no matter what's going on. But the oboe is really hard. Because oboists, part of learning to play an oboe, you have to go through this 5 to 10 year life journey where you learn how to carve your own reeds. And you end up sitting on the tops of small mountains with yetis and old men, bald men teaching you how to, it's really kind of a mystic art how they go about, and when an oboist breaks a reed, it's like you have to have a funeral. It's because they spent so much time carving that reed, right, into the shape of their mouth or the universe or whatever. I don't know. Oboists confuse me. All right. So, did anybody actually manage to get these numbers while I was talking?
Yes. Length is 1.06 meters.
Well, that's the total, right?
Total length is 1.06.
So the long one, I got 0.67.
0.67 and 0.39.
0.39. So when we go to add those together, plus 0.67, right? 1.06 is what I heard. Okay, so there's the length. That's B. That's the answer to B. There's the length of the original pipe. We found the lengths of the two from their frequencies, and then the fundamental frequency of this will be V over twice the length, so 343 over 2, and then the length of the original pipe was 1.60 meters.
161.84.
So I'm going to just call it 162. Right? And there's the answer to A. Again, I don't think the math is difficult. It's like being able to organize the information and understanding the terminology and the context of what's going on here, right? The feedback I've gotten from students over the years is that, yeah, Mr. Balogh, this stuff is easier, but it's still hard. It's like, it's not hard in the sense of like Newton's second law is hard, right? Where like, I don't even still know how to draw a free body diagram, Mr. Balogh. But like here, the difficulty is, okay, in a 10-minute problem, I've got to like organize all the information and know what I'm doing, right? And that's, again, it comes down to practice and exposure and, you know, make yourself flashcards or something to quiz yourself on like what the different terms mean and all that kind of stuff. And you'll actually be okay. Before we go to 2D standing waves, I should point out that closed pipes, well, actually, you know what? I'm going to talk about this later. Let's do 2D standing waves, and then we'll talk about some of the exceptions that are taking place. Stop right there. Okay, so all woodwinds are one-dimensional instruments, meaning that the standing wave just forms along the length of the instrument. So what would a two-dimensional instrument be? The hint's on the screen. Yeah, okay. Percussion instruments, okay, are two-dimensional surfaces on which the standing wave forms. I'm going to play a video here, and this video is going to have a flashing light in it again. They're going to use a strobe light, so if you're sensitive to that, look away. But as a drum head bounces up and down, and they've got kind of like a fake drum head, right? Just a piece of plastic here, okay? Yeah, stop talking and just do it. Okay, here we go. They're going to do this flash, and the flashing lights, just like my string yesterday, is going to help you see the pattern of the standing wave. So here, like the entire surface of the drum is bouncing up and down, right? And then this is another pattern where there's actually like a nodal line, like a nodal surface that exists, right? Okay. And then here's a different pattern where there's a nodal line that cuts across the surface of the disc. Luckily, we're not going to do any of the math of this because this is really, the math gets much worse, okay? But you can have two-dimensional standing waves, one dimension for like pretty much any trumpet, clarinet, trombone, doesn't matter. They're really just forming a standing wave along the length of the instrument. But when you get into drums and other percussion, where the entire surface is vibrating to make the sound, then you've got a two-dimensional standing wave. This is a demonstration where they have a plate, a metal plate here, and they drop sand onto the surface of the plate. And the standing wave pattern, the two-dimensional standing wave pattern, can be visualized because the sand will always collect where the nodal lines happen to be. So if they adjust the frequency of the plate, you change the standing wave pattern on the surface of the plate, okay? And then the sand will go to the places to gather along the sand can't be where an antinode is because the surface is just jumping up and down too much. So the sand will collect along the nodal lines. And lots of different very complicated patterns for this square-shaped plate. But if they go and maybe change the shape of the plate, aha! Okay. Now we start to see maybe some of the reason behind why different instruments sound the way they do. So a violin or a guitar, a stringed instrument, okay? If you take a guitar string, you take a violin string, and you just separate it from the instrument and play it in air, just like tighten it up and flick it or bow it, it doesn't sound like much, okay? It just sounds like a vibrating string, but there's no richness or anything to it. A violin takes that vibration of the string, couples, so you got standing waves on the strings, first of all, okay? Those standing waves couple to the body of the instrument, and the whole body of the instrument begins to vibrate, which then starts vibrating the air inside of the instrument, and then those vibrations start pushing the air molecules around the instrument. So standing waves in the instrument coupled to traveling waves in the air, which eventually arrive at your ears, and you go, oh, violin, or oh, music, or oh, middle C, or A, or whatever, right? Like your brain, however it's been trained to hear music, will respond to that music. So over time, just ingenious people learned what shapes made the best kinds of sounds and how to get those sounds into the audience. And the reason that you have to have like 6,000 violin players and only 2 trumpets, okay? It's because the violin all by itself isn't that loud of an instrument. Like you try to play it as loud as you can, and it's just not that loud. But a trumpet cannot play softly. Like, it's impossible to play a trumpet softly, because what are trumpets for? Raising the dead, or calling the cavalry in, or something, right? Like they're designed to project sound, right? Long distances. You don't ever see people charging into battle behind a violin, right? And there's reasons for that, okay? So, what is music? Like we can talk about musical genres, we can talk about the people we like listening to, the artists, all that kind of stuff. That wasn't my question, right? What is music?
It's one of those questions where we don't really
No, actually, we do know the answer to this one. And how do you tell the difference between music and noise or any other sound? So this is something that is, again, cross-cultural. This is something that unites us as a species, irregardless of where we grew up or what we started listening. Now, culturally, we may have likes and dislikes for certain kinds of music. If I went in here and I played some of the Asian musical instruments and scales, if you've been primarily raised in the United States, you'll listen to it and go, oh, that sounds weird, or it sounds funny, or like it's different, right? It won't sound like maybe some of the Western music that we're used to. Because we have a 12-tone scale here in the West and in Europe, and then Asia's got they've got 15 and 7, and they've got quarter tones. There's a bunch of things going on. It's really interesting. But no matter what your cultural preference for the type of music is, every human being knows when they've heard a musical sound compared to just a noise. And this seems to be a very ancient ability. Everybody's brains in MRI machines responds the same way to musical sound. Again, there might be a cultural preference for how the notes are arranged, but like the actual sound of music, not the musical of Julie Andrews, but the physical sound of music causes our brains to light up with activity. Noise is what when we hear noise, our brain knows that it's noise because there is no pattern to it. I'm not talking about your parents yelling at you, turn that noise off, right? I'm talking about like true noise. There it is. Do you hear the white noise in the room? The fans and the projectors? That's noise. Your brain almost automatically, until I call it out, your brain almost automatically just removes it, right, from the situation. Plus, I'm being loud and I got more decibels than the fans do and all that kind of stuff, right? So that gets back to sound intensity. But like noise, any kind of staticky sound, right? That sound, right, that comes out of something that's not quite connected right, or comes out of a fan or something like that. That's noise. And if we look at the waveform, a noise waveform is like random. Okay, it's all over the place. The frequencies are shifting, the wavelengths aren't consistent, all of that kind of stuff. But a musical sound, something that our brains goes, oh wait, that's interesting, or that's music, is always repeated types of waveforms. Now this one I'm showing you here is a rather complicated waveform. It's got a lot of features to it. It's not just like a sine wave or a cosine wave. Because frankly, a sine or a cosine wave doesn't sound very good. We recognize it as a musical tone. It's just not a very interesting one. That football that I had that I was spinning around my head, that emitted a pure sine wave. And it just doesn't sound good, right? But it's different from true noise, which would be static. So that's kind of getting to the very beginnings and nuances of what makes a musical sound. The tuning fork, that football that I did that gave out the pure tone, a pure sine or cosine function, sounds just like a pitch. It sounds like a frequency, but there's no character to it. There's no musical voice to it. And I am not responsible for the English spelling of this word. I feel like I gotta like apologize about English all the time. That word I wrote on the board is pronounced timbre. We need help in English. Timbre is the word that we use to describe the musical voice of an instrument. A piano's timbre is very different than a flute's. And now we're back to the music I was playing at the start of class. You know a flute when you hear it is different from a piano when you hear it. Flutes, their timbre pushes them more towards a tuning fork. See how this flute waveform right here, it looks an awful lot like the sine wave, but there's some extra added features on there, okay? Whereas a clarinet is starting to deviate even more from that pure sine function. It's all these little things that cause a musical instrument to sound the way it does and to have the timbre that it does. There's lots of physics and acoustics and analysis that can go into analyzing sounds. And one of the way we do it is using something called a Fourier transform. Some of you are going to run into Fourier transforms later on in your studies and careers and things like that, because a Fourier transform is a really useful mathematical device for figuring out all the frequencies in a sound. And so it can be as easy as, this isn't easy, analyzing the sounds that whales give off in their communication. To be able to understand the language of whales, being able to see the different frequencies that a whale sound is producing, the Fourier transform can isolate all the different harmonics and show you the relative intensities of them. Okay? We don't have to do Fourier transforms because, they are mathematically, they're rough, and you usually just make the computer do it. Okay? But these are the Fourier breakdowns. These are the frequency spectra for the three waveforms I just showed you on the previous screen, right? So we had the tuning fork, which just looks like a sine function, right? And then we had the flute, which had a little bit more feature, and then the clarinet that had a lot more feature, right? So if we look at the harmonics of a sine wave, or just a simple tone, okay, coming from a tuning fork, it really only has the fundamental frequency sounding on it. But once you move to a flute, and the way that you produce sound in a flute by blowing air across the mouthpiece and having the correct embouchure, and then having the standing wave couple to the materials of the flute. Some flutes are made out of steel, others are made out of silver, some are alloyed gold, like there's different kinds. And then whether it's an open hold flute or a closed hold flute. There's like lots of things you can do to musical instruments to change their timbre, right? But a flute will always have a characteristic sort of frequency fingerprint, okay? And here we can see that the second harmonic is actually stronger than the fundamental in a flute, or at least this particular flute, okay? And so generally we tend to hear the most dominant harmonic, which most of the time is the fundamental. But in this case, in the flute, you might hear the second harmonic before you hear the first. The clarinet is getting like, you can see how the clarinet sound has sort of pushed the harmonics to be more intense further along. In the case of clarinet, we do hear the fundamental, but these other harmonics come in to cause us to be able to tell the difference between a flute and a clarinet. A flute sounds airy and pure, which is why Camille Saint-Saëns in the music I played for you called the aviary, he wanted to represent birds at the zoo. It was that flute sound, sounding like bird song, right? That kind of those high chirpy noises. Flutes can do that. Clarinets, on the other hand, tend to be more deeper in their sound, a little bit more mellow. Saint-Saëns, I think, used clarinets and oboes to like do the big cats, the lions and things like that, right? Because they kind of have that slinky noise, and cats are shifty anyway. And how's that go? Dogs have owners, cats have staff. I think it's probably a really, really close analysis of what's going on there. And then you have these things, mutes, that you can stick in the ends of an instrument. Did you ever have a mute for your French horn? Yeah, you can use, you'd stick your hand in it. The French horn people will always stick their hands in, right? But did you have a physical mute? You did? Okay, what did you use it for?
Just like for block notes.
Block notes? Yeah, okay, so what were block notes used for? They were just written on the page. What are you asking me for, Mr. Balogh, right? A trumpet, and the physics department won't buy me a trumpet. I keep asking, and they're like, we don't fund hobbies. I'm like, no, science, right? Okay, but what happens when you stick a mute in the end of a trumpet like this is that it becomes a closed pipe. Okay, so a trumpet normally is open on both ends. Remember, an open pipe being open on both ends wiggles with equal amounts, right, on the ends, right? Antinodes on both ends. You stick the mute inside of the trumpet, you form a closed pipe, where it's kind of closed on the front end, but the antinode end is where the lips are doing their thing, right? So what this does to the sound of the trumpet is it alters the harmonics that the trumpet can sound. So when you have the closed pipe, you can only sound the odd harmonics. You've stripped every even harmonic out, and it makes the instrument sound muddier. Not so much duller, but as like subdued a little bit, maybe even quieter, but mostly the tone changes. And especially in jazz music, they will use that sound to get the instruments to sound smoother or sexier. You know, musicians use a lot of funny words to describe what's going on, right? But like it'll just alter the sound of the trumpet. So it's not so brash and it's not so in your face, right? And they'll do it with the trombones and all those kinds of things, right? But these mutes can really change the musical quality of the thing. No, that was those are the ends of my. That's the end of the chapter. So no quiz. It's just I have a template that I leave at the end of the chapter. I always forget to remove it. But that was the end of chapter 17. Yeah, we cheering, right? We're not done with the course, of course. We got a whole new unit to go. But what are we going to do on Tuesday? Exam. What are we going to do on Wednesday? Tuesday is review. Wednesday's a lab. So if you came in late and didn't get a lab, right? Come up here and get a lab, right? Because that's the lab packet for this Wednesday. It's this Wednesday and the next unit. And then on Thursday, we'll be taking the exam, right? So we've got a lot of work ahead of ourselves.